Hi, I'm Jessica, and welcome to today's crash course on the laws of exponents. So today's video is really aimed at secondary 3 students, but if you're in secondary 2, you'll probably find that it's covered in your level as well. And if you're in 4 and 5, you also get it repeated, so it could be useful as a refresher for you as well. In today's video, we're going to be looking at the power of certain numbers, changing the base, the laws of exponents, and then we'll be finishing off by doing a few examples together. So let's get going. So to really understand exponents, we have to go over a bit of vocabulary first. In our exponents, we have a base, we have the exponent, and then we have the power. And the power is our answer. So if you look at my example here, 5 is our base, 3 is our exponent, and the power is 125. It's also really important that you understand that 5 to the exponent 3 does not mean 5 times 3. That is a common mistake that students make. 5 to the exponent 3 is actually 5 times 5 times 5. So the exponent's job is to tell us how many times you have to multiply the base by itself. So it's really just a repeated multiplication of the base. This is a little different when the exponent's a negative or if the exponent is a fraction, but we're going to get to that bit a little later on in the video. We should also, just to help us work through these problems, understand that knowing some of the common multiples of the frequently used numbers is really useful. It makes things a lot faster. So you can see that I've got the first couple of prime numbers here, and you're probably already telling yourself 10's not a prime number, but it comes up so often in examples that I'd put it up there. It's good to know. It's good for you to use because it makes things faster. So now we get to the heart of our video, which is about the laws of exponents. And we're going to start with the exponent 0. When you have the exponent 0, it doesn't really matter what your base is. Your power or your answer will always be 1. So you can see here, a to the exponent 0 will give us 1, and 7 to the exponent 0 also gives us 1. When our exponent is 1, however, then we have to pay attention to whatever the base is because that becomes our power. B to the exponent 1 gives us b, and 3 to the exponent 1 gives us 3. Now, before we go any further with our laws of exponents, let's just remember that we don't want to forget exponent 1 in our calculations. Okay, so even though exponent 1 isn't always written, it's really important to remember that it's there. To use the laws of exponents, we also have to remember that the base must be the same everywhere. Okay, so now we're going to look at multiplying powers with the same base. In this case, you add the exponents together when multiplying exponential notations with the same base. So we've got our example here. Then the first one, we have a base of 7. So 7 exponent 3 times 7 exponent 8. We just have the same base. So we're going to take our exponents and add them together. So we would get 7 exponent 3 plus 8, which finishes as 7 to the exponent 11. When we have a variable as a base, the rule works exactly the same way. So I just rewrite my base. And I'm going to add my 2 exponents, 3 plus 8, for a final answer of b to the exponent 11, just like that. So next we're going to look at dividing powers with the same base. And in this case, we want to subtract the exponents when dividing exponential notations with the same base. In our first example, you can see that our base is 3. So we have 3 exponent 9 divided by 3 exponent 2. And what's going to happen here is we're just going to rewrite the base of 3. But our exponents are going to subtract. So 9 minus 2 will give us 3 to the exponent 7 overall. Now the same thing's going to happen in our second example. You can see that our base this time is a variable. But the only important thing here is to make sure that the variable is the same variable, which of course it is in this case. We've got c both on top and on the bottom. So in this case, my c, it's going to be c to the exponent 9 minus 2. And that is going to give me c to the exponent 7. Just like that. All right, so now we're going to look at power of a power. When a power is assigned an exponent, the exponents are multiplied. So if we take a look at our example here, you see our base 5, and it's got an exponent 3 on it. But then there's a bracket around that, and an exponent 4 on the bracket. So that means that our exponent has an exponent. So this is where we have to multiply. We keep our base, and our exponent 3 is going to multiply by 4. So in the end, what we end up with here is 5 to the exponent 12. Once again, You can probably see me coming with this, but it's going to happen the same way for the variable. So we don't change our base, but we're going to take those exponents, 3 and 4, and multiply them together. So d to the exponent 3 times 4 becomes d to the exponent 12. And we're done. So now we're going to talk about power of a product. The exponent can be distributed when it's applied to a bracket containing a multiplication, and that's what we're going to see here. So if we take a look at what's inside my bracket, I have the multiplication of 3 by 2, and then on the outside of the bracket is the exponent 5. So that means that that 5 actually is shared to both of those bases, which is what we're going to be seeing here. So I just rewrite my bases, only now this time it's going to be 3 exponent 5, and I'm still multiplying it, but it's by 2 to the exponent 5, just like that. In our second example, we have some variables there, and that 5 is going to distribute to the variables in the same way that it distributes to the 8, and exactly as it did above. So in this example, we would rewrite it to read 8 to the exponent 5 times x to the exponent 5 times y to the exponent 5, just like that. So we're going to look at the power of a quotient. The exponent can be distributed when it's applied to a bracket containing a division. And this works pretty much like it did in the previous law, except that you, of course, have a division inside of brackets and not a multiplication. So over here, our 4 over 9, we're going to keep that. We're still going to have 4, but this time that 3 distributes to the 4. So in the numerator position, it's 4 to the exponent 3. And in our denominator, we're now going to have 9 to the exponent 3, just like that. And once again, with the variables, it's going to be the same idea. So we'll keep the basic fraction with e in the numerator position, but this time it's going to have the exponent 3 on it. And we're still going to divide by f, but that will also have the exponent 3. And then we're done. So now we're going to look at the power of a negative exponent. And a base assigned a negative exponent is equivalent to the reciprocal of the base assigned a positive exponent. What that looks like, if you take a look at our examples here, we have 11 to the power negative 3. And when I apply my law, that means I'm just going to write the reciprocal. So 1 over 11, and it's going to be to the power 3, but this time no negative. So I end up with 1 over 11 to the power 3. Here, with my base as a variable, the same thing's going to happen. So right now I have x to the exponent negative 3. That will become 1 over x to the exponent positive 3. The law also works when our negative exponent is in the denominator position. So once again, I'm going to flip that. So instead of having 1 over 5 to the negative 2, I'm going to have 5 to the power positive 2. So I've gotten rid of the fractional representation altogether. Same thing down here. I have 1 over x to the power negative 2, and that is going to become x to the power 2. Now, before I go any further, I have a question for you guys. Which of the following equations is false? If you guessed B, you are correct. So let's take a little moment and analyze why. If I start with my initial problem, c over 2d, and then in brackets, all to the power negative 1. The first thing I'm going to do is distribute this negative 1. So what that looks like is c to the exponent negative 1 over 2 to the exponent negative 1 times d to the exponent negative 1. Now, we just talked about how negative exponents, we have to flip them and make them positive. So instead of writing 2 to the negative 1 times d to the negative 1 in the denominator position, that's going to come up and take over the position of the numerator, and my negative 1 will become positive 1. So in the end, I end up with 2 times d, and my c to the exponent negative 1 is going to come down into the denominator position, and my negative 1 will become positive 1. So I end up with 2 times d over c. And remember I mentioned earlier in the video how when you have an exponent of 1, you don't actually write the exponent? Well, that's what you see here. I've kept my 1 silent. You'll also notice that the real problem with what was said over here is that we had a -2 in our answer. And we don't have a negative anywhere in this answer. So this is the correct answer to our original problem. Let's take a look at a power of a fractional exponent now. Before we go any further, I have another question for you guys. Which of the following equations is true? If you answered D, you're correct. A base with a fractional exponent is expressed as a root, according to the law. So let's take a look at what goes on here. If I have a base of 5 and my exponent is 1/3, what I'm going to do here is that denominator of a 3 is going to come out front here, and under the root sign, I'm going to put my 5, and that will be to the exponent 1. So in other words, the numerator of my fraction comes under the root sign with my base. Now, because it's a 1, I'm not actually needing to write it. So I'm going to just write my final answer as 3 root 5, just like that. Same thing's going to happen with my base x. So x to the power 1/3 will be written now as 3 root x. All right. Now, my second set of examples, you can see that this time I still have a fractional exponent, but I have a numerator that is not 1. So I just wanted to give us a chance to take a look at what that'll be like. Again, the denominator, in this case, it's a 4. So I have base 5 to the exponent 3/4. So it's my 4 that's going to come out front. And I've got my root symbol, my base 5 underneath, and that the numerator 3 is going to come under the root sign with my 5. So I have 4 root 5 to the power 3. In the second example here, I have a variable situation again. So it's really similar to this first one here. I'm going to have 4 out front, and then root x to the exponent 3. Just like that. So let's look at a special case here. If 2 powers of the same base are equal, then the exponents are equal. So what that means is if I have 4 to the exponent 3, and that's equal to 4 to the exponent x, well, you can see that I have the same base, which is 4, on both sides of the equal sign. And I can then conclude that actually 3 is equal to x. So lastly, we're going to look at how to change the base. Before we do, I just want to ask you guys this quick question. The laws of exponents are correctly applied in this calculation, true or false? If you answered false, you are correct. So let's look at how we do this then. Now, you can probably get 6 exponent 5 over 3 exponent 4 another way, but I'm going to show you it with change of base. You'll notice first that because the bases are different, we can't actually apply any of the laws that we've looked at so far. And you'll also notice that 6 is a multiple of 3. So my first step is to break that 6 down into 2 times 3, because what I want to do is get the base 3 in there. So here we go. 2 times 3 to the exponent 5 over 3 to the exponent 4. I apply my law to the brackets here to get 2 to the exponent 5 times 3 to the exponent 5 over 3 to the exponent 4. Now, because I've created the same base situation in both the numerator and the denominator position, now I can apply my law again, and that will lead me to subtracting my exponents, which you see here. And in the end, I end up with 2 to the exponent 5 being multiplied by 3 to the exponent 1. So now we're ready for some examples. In my first example, you can see that I've got a lot going on here. And so I'm just going to take a look at the first part here. That's got a set of brackets with an exponent on those brackets. Then I've got a common set of bases here, and they're being multiplied. I've got another common set of bases here with the b's, and they're being divided. So if I apply my first round of laws, I get led to this point where my 3 has distributed over everything inside the brackets. I was able to add my 2 exponents to get me to -4 here. And this division, okay, -8 divided by 4 gives me the -2 you see here. And I'm able to subtract the exponents on the b's to give me to the exponent 2. Then I just want to separate things out a little bit here. So I'm going to share that denominator out. And it allows me to see what other laws I can apply at this stage. So Next round of laws leads me to here. I was able to cancel out the b's on the bottom. So now I've gotten rid of all b's in the denominator position. And I'm also able to subtract exponents with the base 2. So I have no denominator left in my first term. My second term, you'll see that that exponent -4, well, I was able to move that down into the denominator position here. And my last term, my last set here, I have the same thing in the numerator position as I have in the denominator position. So of course, a number divided by itself just gives you 1, which is why I'm left with -1 there. Last little look, and I can't really apply anything else. So we're finished. Okay, so for our second example, you can see there's a ton going on right now. So I've got this situation here where I've got to essentially undo my root symbol. So I'm going to be left with a fractional exponent here. I've got a division, and then before I do that, I've got this inside the brackets here, a multiplication. It's got the same base though. Underneath, you see a negative exponent. I've got a root sign here, and I've got an exponent on another exponent under that root sign. Everything is to a fractional exponent on top of that. So first thing you got to do is just take a deep breath and go step by step. So applying my first set of laws here leads me to here. I have taken care of this situation. So of course, if I revert that to its fractional form, that would be c to the exponent 18/3, and 18/3 reduces to 6. So that's why you've got this. It's a little more user-friendly than our previous representation. When I add my exponents here inside the brackets, I get 16. And in the denominator position, I haven't touched the -11. I have cleaned up under the root sign a little bit here, so I was able to multiply 3 by 5 to give me 15, and I'm not touching this 81c to the power 7 yet. I still have my 1/2 on the outside of that big set of brackets, so we'll deal with that later as well. Next round leads me to here. If I subtract my exponents, I end up with c to the exponent -10 on top. Still haven't touched the -11 here. I have cleaned up under my root sign. I was able to add the exponents on the c's to get me to 22. And I still have my fractional exponent on the big brackets outside of that, outside of everything there. Okay, another round of exponent laws gets me to this point. So you'll see that I still have my -10 on top. And down here, I really haven't dealt with my -11 yet. But I have been able to take the root of 81c to the power 22, or to the exponent 22. So when I take the root of that, I end up with 9 times c to the exponent 11, which leads me to this point here. The advantage of doing that was the fact that by leaving my c to the -11, you see that I've created this situation where I have a common base and it's being multiplied. And so I get to add those exponents. So -11 plus 11 gives me 0. And we learned earlier how any base to the exponent 0 gives you 1. So essentially, I ended up with 9 times 1, which gets me to 9. I have not touched the -10, the exponent -10 in the numerator position yet, and I still have that fraction outside of the brackets. So I'm going to take that fraction now and distribute it to the numerator and the denominator, which leaves me with c to the exponent -5 on top divided by 3, or over 3. Last step is to get rid of that negative exponent, which leads me to our final answer of 1/3 times c to the exponent 5. All right, so for our third and final example, we've got this scenario here. And the first thing I am going to notice is that, well, my base 6 is actually a multiple of 3. So I'm going to change that base, which you see me doing here. So 6 has now become 2 times 3. It's still all to the exponent 3. And I have also taken that 8 and put it into its exponential form. So it is now 2 to the exponent 3. And all of that is still being multiplied by 3 to the exponent 2x minus 9. The reason that I converted the 8 was for this. Once I distribute that 3, I now have 2 to the exponent 3 on the left side, and I also have 2 to the exponent 3 on the right side, and that allows me to cancel out the 2 exponent 3 on both sides. So now we have no more 2 exponent 3, and I have this common base. 3 to the exponent 3 is now equal to 3 to the exponent 2x minus 9. We learned earlier that when the base is common and they're across an equal sign from one another, it means that the exponents are equal to each other. So now I can get rid of the base altogether and just say that 3 is equal to 2x minus 9, and I'm left with solving for x. So of course, from that stage, I have 12 is equal to 2x, and x is equal to 6. Magic! All right, so that brings us to the end of our crash course on the laws of exponents. I really hope it helped you guys to understand them a little bit better. And I would encourage you guys to go check out the activities that are associated to this video. Until next time, see you guys later.